Hey everybody, we are recording live. We're live from Wisconsin and Bangladesh and Colorado. And Mark is going to be putting the finishing touches on the ecology of forest restoration agriculture tonight, or today, or whatever time it is, wherever you're at. Please put your fingers to the keyboard a little bit later as Mark gets towards the end to ask questions. As you know, he likes to do them at the end. He's going to take as much time as he's willing to give, and you guys want to ask. We have nothing following this tonight. I apologize. Last week, that was me that totally screwed up. We had another session that followed this, which, by the way, was pretty darn good, with Kevin, and you guys are going to want to watch that, and Kevin's going to become a part of our teaching team, and Mark's going to get to know him better, and I think there's some great compatibility that's going to develop there. But anyway, that was me. I had to kind of cut it off to get that started. Mark's going to he's kind of melded that last couple of slides back into today's presentation, and I'm just going to turn it over to him. So go for it, Mark.
All right, thank you everybody for being here. We're going to be talking more on the decay and nutrient cycling in ecosystems, which is all related to soil fertility. We'll get to it through the various different slides we're going through. And then although forested ecosystems, and remember by forested I mean any ecosystems with trees in it at all, from the tundra with dwarf willows and birches to wide open, savanna plains like the Serengeti with one or two acacias here and there. They follow the same general habits of growth and regeneration and so on. So it's applicable no matter how few or how many trees you have. Although forested ecosystems are only 21% of the Earth's surface, they constitute 75% of the terrestrial plant biomass. That means that on this 21% of the land, if we got 75% of the biomass, we have a huge leveraging effect on the whole food, water, carbon dioxide, species extinction nexus, populations included in there. What we do with woody plants in our ecosystems, we produce food, we capture water and manage water and watersheds. We take carbon out of the atmosphere, sequester it in tree bodies, branches, leaves, roots, grasses, soil, and we're providing habitat for wildlife in addition to food and water for human beings. We have a disproportionate large leveraging effect. That's why what we do is so critical, and it's important that we understand how to do things as ecologically as possible and learn in perpetuity as we can. We can feed people and supply for nature. Can do that? If anybody figures out what that word is. Can Big Ag do this? Big Ag does not do this. Big Ag is degrading the resource base across the planet. They are accumulating wealth in the hands of their particular large corporate entities and their shareholders. They are spreading poisons. It's chemical warfare basically all across the agricultural world. And 50% of the human race goes to bed hungry every night. The big ag that wants us to defend ourselves, oh, you can't feed the world that way, they're not feeding the world their way, and they're destroying ecosystems in the process. We're going to restore those ecosystems. The production of plant matter in these forested ecosystems, it influences global cycling of carbon, the atmosphere. It's indispensable source of food, fuel, animal feed, medicines, oils, industrial ingredients, fiber for human populations. You and I are critically dependent on forested ecosystems for our very survival. We're so critically dependent that if we didn't have some sort of source of wood fiber, even if you're using, watch this, I'm going to breathe, even if you're using quinaf to make toilet paper, in order to grow that annual crop, quinaf or sisal, you would have to destroy a perennial ecosystem, a perennial regenerative ecosystem. In order to plant that annual crop, even if you're using hemp, it's another annual plant. You have to destroy a perennial ecosystem in order to grow that at scale enough to make paper fiber. And I don't want to run out of paper fiber. I would rather supply trees to the paper industry and have deer and turkeys and wild pollinators and food and a really cool shade to hang out in and all that kind of stuff. As some questions are coming up on the right-hand side of the screen, I actually have all the functions working tonight. As far as the projects are concerned, get those projects in the next week or two, and yes, you can make changes to your projects and submit that to us here. So forested ecosystems, they are home to countless species, animals, plants, non-vascular plants, fungi, birds, amphibians, and so on. They are the storehouses, the tropical rainforests especially are the storehouses of the most massive biodiversity on the planet. This is where the planet's genetic gold mine is in the forested ecosystems. It's in perennial ecosystems around the world. So now plants, of course, this is a very basic graphic, and the processes that I'll be highlighting here are a lot more complex than even humans understand right now, but it's pretty simple. Plants assimilate nutrients from the soil. They incorporate them into their body using carbon as the energy source and as a building block to form the biomass, the living tissues of that tree, the branches and trunks and leaves and so on. And eventually, some of those branches and leaves fall to the ground as litter. And the bark, and eventually the whole tree falls over too. That's called plant litter. Now, why didn't that make a move? I'm trying to get, here we go. So dead leaves and other plant and animal material, that's the litter that falls to the soil. Of course, the decomposers will break down that organic matter. They're using the energy in the double carbon bonds in the lignin and cellulose, mostly lignin and cellulose in woody material. There's also minerals that are in there that were taken up by the plant that now get released back to the soil. So the decomposers are using the litter for energy and for building blocks as well. When the decomposers function in the soil, they're also exuding acids and other kinds of exudates that help to dissolve the actual parent material, whether it's bedrock or in this case rocky subsoil. So the function of decomposers helps to make the minerals, they're soluble, and then those minerals get taken up either by plants or by the soil life itself. So now the hard, solid matter of the planet now becomes soluble, and it's within living tissue. And then it can be taken up by other parts of the system. And so then, of course, all of these, the rocks are basically broken down and released as nutrients. This process right there of litter accumulation, decomposition, and mineralization of the subsoil parent material, that is where fertility for plant life, and of course plant life is where animal life comes from. This is the big kahuna when it comes to health and functioning and fertility of our plants. It's the decomposition cycle with the litter accumulation, decomposers breaking down organic matter, and then minerals being taken into solution inside of plant and animal bodies. And then another source of nutrients for our woody plants, of course, is interception of things coming in from some kind of precipitation. Remember from a few weeks back, dry precipitation and wet precipitation, water dripping through, running across, rainwater running across, lichens, epiphytic lichens such as reindeer moss and Spanish moss. There's lichens on the trees. Every time that water passes through those, it's picking up some of the exudates from the lichen, which is, you know, a symbiotic algae fungi combination. That's what's also contributing nutrients to our woody plant system. So this right here, these are the things that we want to deal with. We want to have interception. We want to create a surface that it has more area exposed to the wind and the rain, because that tree is going to be picking up more atmosphere if it has more surface area exposed to the air. And atmosphere, of course, that's the carbon dioxide building blocks. It's all part of this process here. It's going to be picking up more rainwater, which has dissolved minerals in it already. Has a lot of nitrogen in it, because nitrogen gas is like, I think it's 85% of the atmosphere. So this whole entire combination here of the litter, decomposers, mineralization of subsoil and parent material, and then of course interception, precipitation from the outside. This is the fertility cycle of a perennial ecological system. And all you got to do is look at these various different things, and you'll see that the whole entire system is limited or controlled by the same processes that will affect one individual plant. Over here on the right, it's high temperatures during the daytime, extreme shortage of moisture. Over here on the left, we've got low temperatures. We also have low angle light, because we have these real tall, narrow forms in order to get that low Arctic light. Low temperatures, low angle light. Here's on the equator, we get these high angle light. Also, moisture is an issue. Excessive moisture in the lower part. Seems fairly evenly moist up on the right. The factors influencing Wayne's plants that he's putting in the ground right now, his Korean pines and his hazelnuts, are the same factors that affect the whole entire system. Now, this is part of the magic of woody plants and the economy that we're building. As restoration agriculture ecologists, we are designing perennial ecosystems that ag-grade through time. They actually create a more diverse and fertile soil. It favors habitat for a more diversified flora and fauna. And every year that tree grows, that's a positive net gain. You put a tree in the ground, next year it's going to be X% bigger, and so on and so on and so on. It does it all by itself, almost completely passively, and it doesn't cost you a penny once it's in the ground if you treat it that way. That's pure, almost incalculable economic gain. And of course, plants that are adapted to a specific set of environmental conditions. You wouldn't want to try to plant saguaro cactus up at my homestead in Alaska. You would not have all that much success. You would not want to plant acid-loving blueberries from this patch out here in Alaska. You wouldn't want to plant acid-loving blueberries in a place like Plitvichka Lakes, which is super, super alkaline because the water has supersaturated calcium in it, so much calcium that when the water comes out of the ground, it no longer is able to hold the calcium, and it precipitates out into terraces. You wouldn't want to put one of these water-hungry plants over here, and vice versa. That's why in restoration agriculture we emphasize over and over imitating our natural plant communities, and of course selecting for the ones that produce our food, fuels, medicines, and fibers, and plant the ones that are always found with one another. And that will give us the highest chance of success, because those plants will be most competitive on that site. Yes, you can grow bananas in Alaska if you want to. At what cost? You can grow blueberries, you can grow Labrador tea, cranberries, lingonberries at zero cost. All right, now this is some of what I want you guys to think about. I'm going to spend a pretty good amount of time on this. Is that the maximum photosynthetic capacity of trees is generally lower. And so if you think of a race car that will go, like the engine will go at 10,000, and woody plants are more like pickup trucks. They got a Chevy 350, and then once you get up over 4,000 RPMs, you're going to blow that thing up unless you put a lot of money into that engine and worked it. They just run at a little lower rate. But that also tells you a little bit something, is if you've got something like a sprinter who's running the 100-yard dash, you take that sprinter and you have them run at the 100-yard dash speed for a marathon, and they can't do it. They just can't hold up that long. They end up blowing up. So with our annual plants, this is maize, for example, planted sometime in April or May, it begins to grow. The June 21st in the Northern Hemisphere are the longest days of the year. That's when there's a maximum sunlight here at latitude 50. Maximum sunlight is back here in June 21st. And isn't it interesting that the corn plant hasn't even reached its full size yet? It's still building the plant. It's not even pollinated. It's not even growing kernels. So it's spending, you know, this early part of the season, almost half of its growth, half the season, all that photosynthate just goes to build the plant. Then it has a few weeks where it's one of the more efficient plants at converting sunshine into carbohydrate that's out there on the planet. It's not the tops. I think for terrestrial plants, potatoes are way up there, and cattails are also way up there, but those are more aquatic than purely terrestrial. So if we've got this corn plant, and this is the area that it's taking up, this is the amount of photosynthate that it captures, including the stem and including the kernel. So if you do that basic little math on a triangle here, half of the base times the height. You know, the height is 14 hours here in the summertime, times the base of 4 months. So half of 4 months times 14 hours is 28 month hours of photosynthate. Of course, the word month hour of photosynthate is just to give us a label, because that's what this is. For that many hours of that many months, that plant has been photosynthesizing. So 28 month hours of photosynthate is what that corn plant, that maize plant, can capture. Well, now let's go to a tree. The trees aren't as high. They don't capture as much of that sunlight. So here, if this is 50 degrees latitude, you know, there's only a little quarter of an inch of space here. That corn is taking up so much more of that light when it's finally there. But you look at the trees are photosynthesizing whenever it's not freezing out. And if you just take the bark, thin bark of a branch, and you scratch it, it's green underneath. That is green, and the cambium layer is photosynthesizing. Wood cells up to 3 years old inside of a plant are still photosynthesizing, albeit very slowly because it's rather shady when you're 3 years deep in the wood. So what is the area of that particular, the sunshine that tree could capture? Half times the base times the height is 9 months times 8 hours a day. That's 36 month hours of photosynthate. So that's more than the corn was able to synthesize. I'm going to get my tang tangled up. You just watch. So 36 month hours of photosynthate, and it's less efficient. That pickup truck did more work than that race car did. Well, now we also have to include the ephemeral plants, these little ones that just come out in the spring. We just had ramps. They're almost finished their peak. They're now flowering and about to set seed. Things like stinging nettle. We've got all of our spring ephemeral plants, of course, most of which are spacing me out right now. You know, dandelion, nettles, ramps. We've been eating those all spring. So we can capture a little bit more. And all the other plants are also photosynthesizing as well. We don't necessarily need them for food. They're also part of the fertility cycle. So we add these 2 month hours for that right there. And then we have the summer ephemerals, the understory plants that are living in the summertime, for another 4 month hours worth of photosynthate. And then, because we're doing this in semi-open alley crops, let's grow some annual plants. So here we're going to plant, we might as well just say we plant maize in our alley crop system. We've got trees, we've got understory ephemerals, we've got understory shade tolerance here. I didn't include any vines in this because we could get as crazy and complex as we want. I think we really need some hardcore research on total available photosynthate in perennial polyculture systems. But if we do this, we figure out the area of the annual crops, we'll notice that we got 20 month hours worth of yield out of maize in this alley cropping situation. But wait a minute, oh no, we just had a 30% reduction in annual crop yields. You can't feed the world that way. Ah, what are you thinking, you crazy permaculture, restoration agriculture people? You're just telling me to plant a system with 30% reduction in annual crop yields? Yeah, I am. Yeah, I am, because we're going to get 36 month hours out of the trees, 2 out of the ephemeral springs, 4 out of the understory, and then 20 from the annuals. We've got 62 month hours worth of potential photosynthate in the system here. That's more than double the potential yields of an annual crop system. It's State University of New York did research a number of years ago, some of the pioneering research on total photosynthetic flux in a system. They did it for short rotation woody cropping systems, which was for willows for biomass, hybrid poplar for biomass, etc. And in some of their trials, they showed that woody plants that were grown for a short period of time, cut to the ground and regrown, they actually captured between 3 and 7 times the energy per acre as an annual crop field. So if we're only doubling the yields of an annual crop system, that means we've got another 100% more, if not 700% more total yield that we can get when we start to capture more of that energy with our perennial system. If we look at this line, this curve, this red curve line here, in theory, if we got a really, really densely, tightly stacked system, we could have all kinds of plants stacked in the system to capture more and more and more of that sunlight. Well, if we don't have plants in there to capture more of that sunlight, let's have, for yield for harvest and sale, let's use these other plants as the energy source for our fertility cycle. And that's really critical as part of what tonight's session is all about, is we want to be talking about how to capture the energy of photosynthesis and turn it into fertility. And so, yeah, this doesn't even count animals or fungi in this particular system. Now, we've also gone through in weeks past and learned that with more sun, but not too much sun, if we're in the full shade, our woody plants won't photosynthesize fast enough. So we want to have them with more sun. Our sun-loving plants like oaks and aspens and pines, when they're in the full sun, they're running at full speed. So whatever architecture we set up, we don't want the plants to shade one another too much. We want them to be full sun. We also want our grasses to have enough sun, so we want an open system so we get everything from grass and ground layer plants all the way up to canopy layer plants on that whole system, so we can maximize sunshine. That's all about our canopy architecture. We want to have this deep architecture so we can capture lots of air. It's exposed to air all around, and it's exposed to sun all around, and we have our grasses growing vigorously underneath. That's at New Forest Farm. And of course, air temperature directly controls how much carbon we take out of the atmosphere and how fast our trees operate, and our shrubs and bushes and vines, etc. We want to make sure that there's full enough sun so it runs well, but not get too hot. So once it gets past this range of 20 to 30 degrees Celsius, and somebody who has their fingers free in a computer can, if they'd be so kind as to let us know Fahrenheit temperatures on that. Once we get up above 75, 80 degrees, photosynthesis slows down. And sometimes you'll begin to, if it gets too hot, the plant will actually lose more carbon dioxide to the atmosphere than it gains from the atmosphere. That's putting it into a net backwards situation. You can plant trees or grass and actually off-gas into the atmosphere. And of course, what is critical is water. Without that water, those plants won't grow. And that's especially important, like in Wayne's situation out in Colorado there. If it rains 10 inches per year, we don't want that 10 inches of rain to run off the ground, which has been the situation because we haven't, his property, the majority of it, the slope hasn't had any water management structures put in place. So of that 10 inches of rain, let's get it to soak in. Whenever snow is there, let's have that snow melt in, because that's going to help our plants photosynthesize faster. And this is just a system that we installed last fall. If you guys look up Hawk Journey Farm, they post pictures fairly regularly of the system right now. The grass has come in spectacularly beautiful. The pond is about half full. The reason why it's not completely full is this line right here needs to be expanded across this driveway and start capturing water from the other side of the field. That would give it more water to fill the pond faster than the pond fills. Comes out this way, and it spills as an even sheet across, off of here and off of here, spills in an even sheet. And so because this requires cutting across the driveway, we haven't done it yet. We want to wait till everything's all grassed in and secure before we start doing any more cutting. As a tree grows, it'll eventually reach maximum size. And remember, I was mentioning dark photosynthesis versus light photosynthesis. Well, dark photosynthesis is just regular respiration. Our cells, just by staying alive, are using oxygen and giving off carbon dioxide. The same is true with plants. Their cells use oxygen and give off carbon dioxide. Well, the chloroplasts, of course, use carbon dioxide and produce oxygen, and they also bind the carbons together into sugars, both simple and complex sugars. That becomes energy. Well, as a tree gets to be a certain size, there's so much living tissue in this tree right here that it's almost at break even. That it's taking in as much carbon dioxide as oxygen's giving off. It's taking in as much carbon dioxide. I mean, as much oxygen. It's taking in as much carbon dioxide and turning it into as many sugars as it can, but then it's using those sugars right up, and so it's not making any net gain after a while. Trees like this is El Castaño de Centocavalli, gigantic redwoods, actually may be at a state of carbon off-gassing because the wood is starting to decay and it's releasing its carbon dioxide to the atmosphere. This tree right here still does, has the largest trunk diameter ever measured on a tree, but the once upon a time gigantic tree part of it, has burned out and is rotted out. It's almost gone, so this is just a ring of stump sprouts that's remaining anymore. So at a certain point in time, once they hit maximum size, they don't make any net gain anymore. Well, the net gain is important to us because we want to have a surplus of carbon on the site because that's the energy that we use to fuel our decomposition rate, which is what's helping to mineralize the substrate, the parent material, which gives us additional flush of nutrients into the system, which allows our plants to grow faster. If we want to have our system really humming along fast in the maximum productivity state, we need that energy to run on the gas pedal. We don't want to just kind of hold it steady state and sit there like this tree is. Although this is pretty fabulous 4,000-year-old tree, it doesn't have a lot of extra surplus stuff to share. Here's an interesting example. I hope I put these. I just added a whole bunch of stuff later this afternoon. I've showed this slide a couple of times. This was white oak, white and red oak, chestnut and black walnut. The walnut was planted direct seeded right into the ground, thrown into the ground, and then there's hybrid poplar in there. And we've grazed animals in there for 20 years. That maybe once or twice in the summertime they go through that system. And what happened from across stage left here, across the street, there was a bunch of Robinia black locust that has thrown seeds in there, and the black locust grew up like crazy. And this winter that I started to thin it out because I want more sunlight to reach my nut-producing trees because I want the nuts for human consumption and for animal consumption. And so I removed a whole bunch of the locust poles, have gone through and chipped up many of the branches to let in more sun, to let the grass come back so I can have more animals in there. All of the brush that you see here is surplus energy that this site stored, and when I've removed the competing Robinia, it will release the trees that I had left behind, the oaks and the walnuts and chestnuts, etc. They'll grow faster. Obviously, there'll be a nitrogen flush from the roots of the locust as well. And the grasses will get more sunlight and they'll grow more vigorously. So this is all surplus energy. The wood piles here, I'm going to use that energy to heat my home, and we're going to use this energy to crank up the soil life. And thanks for posting the 30 degrees is 87 degrees Fahrenheit. I took this picture here because this was one of my permaculture zone 5s that when we first bought the farm, it was all either crop fields or open pasture, and we just let one corner go just to see what it would do. And so this right here is 22 years worth of doing absolutely nothing. First of all, thorny brush came in, and then some sun-loving plants got established. This is white ash. We had some American elm is in there as well. and then some hickories, smooth bark pignut hickories are in there, and then just now there's some basswoods and maples, the shade tolerance, coming up underneath. This is all that that system has yielded in 22 years is a bunch of brush and like 5 trees, whereas back here, whereas we planted it with a high density of our desired species, which is our chestnut, walnut, oak, and our hybrid poplar, it came, all the prickly brush came in just like this did, but we got, you know, approximately 300 pounds worth of beef per acre per year. In year 10, we got multiple thousands of board feet worth of poplar lumber out of it. And then this year, I think I'm up to 3 cord of firewood right now. And each cord of locust, I think, is around 4,000, 5,000 pounds for a cord of locust wood. So, you know, 2.5 tons of hard, hot, wood-burning, woody biomass on that particular piece of ground. So this was a system that has yielded, and there's more useful plants left behind. There are nut trees in there that I can eat the nuts from forever, and the locusts are all going to sprout back. Many of the poplars that I cut down, they're going to sprout back. Obviously, I'm going to be making mushrooms with them, et cetera, et cetera. I'm feeling like I'm repeating myself. One of the things is when we know how trees will allocate their carbon, we can understand how to use chop and drop, how to use management of our decay cycle, how to use grazing in order to allocate the excess nutrient into the direction that we want it. We can allocate the photosynthate of that tree towards root production, towards stem production, towards reproduction, which is, you know, the seeds and fruit, or to chemicals to deter herbivory. And then just shows a Scots pine tree. There's tables like this for many different types of trees. This is the one that I found. But if we look here, we will see that of the photosynthate, 55, 61, almost 62% of the tree's energy goes towards growing roots. What does that tell us? If you got 60 some odd percent of that tree is going towards root energy, the real action in a tree, a woody plant, a shrub, is below ground. We need to understand that, and we can take care of that. Now, if we have our system running, low light, of course, will slow down photosynthesis, and even when the soil is rich, the trees will no longer, they'll no longer put energy towards making stems. The stems will start to get small. You'll start to get disease in there. They don't make as many chemicals to defend against disease and pest attacks. They start to fall apart and die. This is the stem exclusion phase of a woody plant system, and it's right at this phase here where there's a whole bunch of magic happening with our decomposition cycle. If we keep our place at a stage like this, it's wide open. We have the opportunity to graze it. We still have wood available to us. The plants will allocate their resources to different things when there's abundant photosynthate available. When there's enough sun, go back here again, boom, they're going to start putting it into seriously heavy roots here. This just talks about how fertilizer helps trees. I think we all know that some sort of fertility helps trees. This was a system, I've showed this a couple times, I've got some updated pictures with it, that 22 years ago, this pasture was all the way up into to this edge here, and these trees, these darkest, largest trees, were about as big as this brush is here. And so in 22 years, I've done no brush removal. We've grazed cattle there. Well, as these trees have grown up, they've now stopped the sun, or they've blocked the sunlight from the forest floor. So at this place here, I probably could have, should have, whatever, thinned this out 3, 4, maybe 5 years ago, and I could have kept the grass growing, but I didn't get around to it. I've only got 110 acres to take care of, me, myself, and I, all by myself, all at once with no money. And so, you know, things sometimes grow too fast for you, which I'm okay with. So what I did is I went through and I dropped all the trees that were not desirable. And you got to understand, the desirable thing is purely a subjective choice. It's a human choice based on my values, and I'm growing food for myself and feed for animals. So I want all the nuts producing trees. There's hickories in here. There's apples, oaks. And then, of course, I want the grass that the animals can graze. The larger diameter material I took as firewood. The smaller diameter material will drive over it with a flail chopper and chip it all up. And that's just what it looked like. One chainsaw worth of gas. It's not too much work. See a nice little hickory tree here. This is part of the seed that dropped in. This is an oak, and that's an oak. There's a whole bunch of maples back there, some more hickories. That's what the brush looked like on the ground. This is, I think it was last October, looking at the leaves. And you can just go ahead and count this when you're doing the replay, that the average size of these trees is 10, 13 years old or so. And that's basically the size of firewood that I burn. I don't burn a lot of big, huge trees because we've got so many little trees growing, and I'm using those to manage. I'm managing those to help the growth of the larger trees so they'll grow faster. So now that I've removed all the competition, these oaks that we see and the young hickory that we see, they'll get more sunlight, and then all of the nutrient released during this decomposition process. And the carbon is the energy source that will get the decomposer organisms, the soil life, going. The soil life is what helps to release the minerals from the bedrock, and so then all the trees can take these minerals up. So this is that cycle of the litter, the decomposition rate, and the soil mineralization. So then after the flail chopper goes through, that's what it all looked like, chip it up pretty fine. This was 2 or 3 weeks ago, as it started to get warm. On this particular area, I did cast some seed. I got a mix of various different grasses and clovers that were in there. And then I believe, oh yeah, this was also a couple weeks ago, I got some shiitakes that are sprouting on their own. Of course, shiitakes theoretically aren't supposed to escape into the wild, but they do. And they're decomposing, releasing their nutrients to the soil, or they're releasing their nutrients to me because I like to eat them. And then we've got all these, you can see the little clovers and some of the grasses started to sprout. It was about 2 weeks ago. You can see some of the stumps left behind of the trees that were the undesirable trees, some of the residual grass that was already there. And then this was just taken this afternoon. And so you see it's gotten a little bit warmer. So this whole area has been chipped over, this the most aggressively, obviously. And you can see how the green haze going in there as the grasses are greening up. And here's you can see all the little grass that's growing in there now. This is going to be a beautiful pasture. I'll keep taking pictures of this through the summer just to show you guys how it greens up. So other organisms also influence the carbon and the nutrient cycling in our system. So what we were just talking about right there was litter. We have these plants that are accumulating an excess of carbon, or extra plants that are accumulating carbon for us, that we tell it when to become litter because we're in charge of our pruners and our chainsaws. And then we have animals that are coming in, and they're also going to be eating organic matter, grasses and browse, and they're going to be pooping and peeing, which is part of our fertility cycle. The growth and metabolism of our decomposers and that of the animals is fueled by the organic matter produced through the net primary productivity. Now, we spent a little bit more time on NPP a few weeks ago, so I'm not going to go too much into it today, but it's the difference between the total photosynthesis that goes on in a plant, its own personal uses, which the next slide will show, and then herbivory and litter fall. It's the net primary productivity that's left over from the plant taking care of itself that's part of our fertilizer. And these are the guys right here who are helping to release our fertilizer for us, the decomposer organisms. I like showing the edible fungi because I really like to eat them. First one is lion manes, oyster mushroom on a poplar stump. Now cattle, here's my preferred herbivores in a system like this. Of course, I like pigs as well too. Chickens, sheep, try to stay away from goats because they will be extra good at eating your trees, better than pigs, chickens, cows. And this is another herbivore right here because this will take down green material, not just chip the brown material. That's my flail chopper. When we do this, we can inoculate with our own preferred decomposer organisms. Just for general chips, when I'm doing something like this right here with the flail chopper, I like the wine-cap stropharias. I get my stuff from Field and Forest Products in Peshtigo, Wisconsin. A friend of mine has been doing that. He's been in the trenches for years and years and years. It's finally to see him somewhat successful. And all these leaves, these are last year's leaves that are now going to decompose extra fast because I got them and I've chipped them, shredded them up. Now they're going to have good full ground contact, and they have pre-inoculated with mushroom spawn. They're going to decompose and release their nutrients quicker to my crop. And there's some of the delicious aftermath before the cows get in there. Now, this is what we were talking about. I was talking about earlier. We got the gross primary production is the photosynthesis. The leaf has to, all the cells respire on its own. It has to build and construct itself and maintain itself. And so what's left after it takes care of itself and just respires is the net primary production. Now, out of that net primary production, we've got the plant itself accumulates biomass. The tree gets bigger. But it's also getting eaten. It's getting eaten by insects. It's getting eaten by cows, sheep, pigs, etc. Then it gets assimilated into their bodies, and then those bodies can get eaten by other bodies. Let's say, for example, the leaves get eaten by a caterpillar. Caterpillar, while it eats, is pooping and peeing. Well, then it gets eaten by a bird, which poops and pees, which gets eaten by a raccoon, which poops and pees, which gets eaten by a fox, or a coyote rather, and it poops and pees and so on, and then the coyote gets shot by the hunter because the coyote was going to eat the chickens. All of that life and the excretion of these nitrogen compounds, that's all fueled from herbivory on this system, and that's where we get a lot of our soil nutrition, is through this the herbivory pathway. Well, then there's the whole litter pathway. That's the branches, the leaves, the bark. That's the chop and drop as this decomposes. So if you can't see me when I'm covering the screen, but if we were to cover this whole thing right up, look, there's more action and there's more energy going on in the secondary processes than there is in this primary process. It's pretty simple. The tree grows, it constructs new tissues, it takes care of itself, it just respires. Well, then everybody eats it, or stuff falls off of it. That's what's driving the system, is that surplus that tree is producing. And that's what we want to tie into. So think about a annual crop, for example, that is, let's say, maize on ground, and they give it a nitrogen fertilizer to allow it to grow. All of the soil minerals and nutrition and the nutrient cycling that could have been there is gone. There is no cycling of nutrients over and over again. What was once upon a time a tree leaf has now become rabbit flesh, and the rabbit is pooping and peeing. Well, then a rabbit gets eaten by a hawk, so all of those nutrients that were rabbit are staying in the system, because then the hawk is still around our system. Maybe the hawk eats a snake. Looks like the hawk's eating everybody. And eventually the hawk goes down. All of this represents this net primary productivity, this net ecosystem productivity, excuse me, that is now kept in biomass. This is what it's all about. Our amazing amount of fertility is in the life itself, the soil life and the above ground life. And if we're really doing our system well, and if we're only selling seeds, for example, let's say we're going to sell chestnut seeds. A chestnut seed is mostly carbohydrate, carbon, hydrogen, and oxygen. We grow this system, and it aggregates. The soil is becoming richer, more species diversity. The total nutrition available on site is way more than what it was when it was just corn and dirt. And if we're just selling chestnut seeds, carbon, hydrogen, and oxygen, we're just shipping the energy off the site. We left the nutrients on the site. It becomes richer and richer and richer through time. So if any disturbance that goes through a system reduces or eliminates the live biomass accumulation, go back to here. This right here represents richness in that system. It represents stability in the system. Any system that gets rid of that is in a stage of degradation. And the total productivity of that ecosystem is negative, and the total biomass declines. That's in a process of degradation and can support less life through time, less and less and less life through time. Annual agriculture is in a stage of ecological degradation. We took a rich, three-dimensional perennial ecosystem that was accumulating total biomass and nutrients, liquidated it, and now every year they're oxidizing the soil more and more and more. The organic matter in the soil is being depleted. It's off-gassing into the atmosphere. There's less and less nutrient availability because there's no more soil cycles going on with all the decomposers. This is in a state of ecological and nutritional freefall. So how many calories of fossil fuel per calorie of corn? How many calories of fossil fuel per calorie of corn-fed beef? Off the charts. If it's 10 calories of fossil fuel for 1 calorie of corn, and 10 calories of corn to make 1 calorie of beef, that's 100 calories of fossil fuels for 1 calorie of beef. Where is the nutrition if all we're doing is adding NPK and we're not mineralizing the parent material of the earth itself? Carbon is the energy that fuels the biomineralization of the parent material, and it is what is the whole source of this biomass accumulation. The more carbon flux in our system, the more life that system can potentially support. So if you remember back to that graph with the bell curve with the amount of sunlight available, the more biomass we have in there, the more carbon flux we have in there, the closer and closer and closer to that line we get where we can be optimally utilizing all of the sunshine striking the planet where we are. So of course, because most soil organisms get their energy from the decomposition of plant matter, that means that decomposition is what it's all about. So during decomposition, the plants use this energy to build their own biomass, and then the rest they excrete. Yeah, I was trying to say poop and pee, but like a fungus doesn't poop or pee, but it does excrete. They get rid of all these different things, most of it as ammonium, which is immediately assimilated by plant roots. This is where fertilizer comes from, not from a bag and not from natural gas somewhere or a mine. So biological inputs of nitrogen to our forested ecosystem happens through soil bacteria, fungi, tree roots, free-living bacteria in the litter, in the mineral soil, epiphytic lichens, animals, and the decay of woody debris. This is what it's all about. It's not the topsoil. It's not, these special stuff from a bag. It's litter accumulation. It's herbivory and the whole secondary consumer cycling over there. It's the decomposition rate. It's the epiphytic lichens and fungi, the free-living bacteria in the soil. It's the whole system together that makes it work. It's a complex living system. It's not one magic bullet to make it work. And all we're going to have to figure out is all we have to do is if we learn these basic principles, we're now the managers of complexity through time. The decay cycle is what drives the system. Free fertilizer. When we manage the timing of our litter deposition and how long it spends in the system, if you don't want that stuff to decompose, if you make a brush pile, for example, that brush pile can dry out. And it may be there for 10, 15, 20 years. If you want it to decompose right away and get a flush to your trees, that's all right. I'm going to stop for a second because I see this notice from Stephen Bradley. Did I really lose sound? If I didn't lose sound, tell me.
You sound good to me.
Oh, thank you, Mark. All right. So in order to manage our growth cycle of our system, go back to those oak trees and the walnut and the chestnut trees. If I want those guys to grow faster, I have to have a good hyperactive decay cycle, releasing all those nutrients for my trees. So the timing of it, water management, temperature, organic matter, that's the magic of it all. And what's so cool about it is we can sell fungus if we want to, or we can eat fungus if we want to. Guess what I had for dinner? I had morels, not shiitakes. All right, back to some timing here. Following a disturbance, the biomass has been reduced close to zero in disturbance, whether it was a windstorm, a fire, a clear cut in that case, or tillage by a piece of equipment. That system has been set back successionally, and now it's going to start over again. And the overall living biomass of that system is going to take some time to get built up. Once it's built up to an optimum level, it'll be at its high rate of speed. It's really going fast, and it's when it's at that stage that we can maintain it there. And at New Forest Farm, it's 22 years now. I think it's probably at hyperactive speed right now, and I think that if we just maintain it at this canopy closure, that's probably close to the optimal in many places. There's some places that are still growing in, but it's at the optimum rate of speed, I guess we'd call it. So eventually it'll go from disturbance back to a mature forested system of that type, whether it's a Michigan beech forest or whether it's high altitude Rocky Mountains or Himalayas or Africa. Different plants, different physiognomy of the system. It takes time for that to build back. What these slides show, and there's been a lot of research, especially in the northern White Mountains of New Hampshire, is forgot what the heck the name of the forest unit is called, but more research has been done on that particular, Hubbard Brook is what it was called, on the effects of soil and soil nutrients after cutting, after a clear-cut situation. When you remove that overstory, whether it's a light thinning cut or a clear cut, automatically there's going to be a whole bunch of decay going on. It's going to really ramp up the decay in the soil, on the surface, and there's going to be a flush of nutrients available. What happens in a situation like a plain old clear cut, like back here, or in the case of when you're tilling the ground and the rain hits it, all your nutrients wash away. At this time of year, right now in Wisconsin, all the streams smell like cat urine. Well, the cat urine that you smell is urine. It's nitrogen. It's all the fertilizer that's leaching out in all the rains. If they had put on anhydrous last fall, that's where a lot of it is. And in a clear cut, a lot of those nutrients will leach away as well, because there's nothing there to use it. You got to be, have something there to use all those nutrients. So we know that after disturbance, there's a big flush of nutrients available in the soil, and we can use that as a tool. We can use that as a tool. We know that our system is going to go from being a young system, it's going to grow through maturity, through however many years it is, and we'll know that if we were to cut this system down here on the right, that all of a sudden it's set back to here, there's going to be a tremendous flush. All these roots are going to decompose, and there's nobody there to utilize that nutrient. So it's lost if we don't capture it somehow. And so that's why we do the agroforestry techniques that we do to always have some sort of woody cover there to capture it. That's why we also have grasses in the system. So we have the thick grassy roots to soak up any nutrient that might be trying to leach away. Excuse me. Just prior to canopy closure is when that plant is photosynthesizing to the max. And that's the amount of carbon that can be fixed in that system. There's only so much carbon that can be stored on a site. White pine, believe it or not, from what I've seen, white pine is one of the larger total amounts of site carbon that's been sequestered. It's right up there with redwoods, believe it or not. We don't necessarily want to get to that canopy closure stage. That may be the total amount of biomass that can ever be there, but if we have, I was just going to use 30 tons, I think it was 30 tons per acre of pure carbon in a white pine system. If 30 tons is the maximum you could ever possibly get, well, once you hit that steady state, that closed canopy of the 30 tons, you can never gain any more. So if we always keep our system just before canopy closure, it's always in that high rate of speed with almost as maximum amount of carbon we can have on the site. And then when using that carbon, and we can remove that sustainably, because we're keeping that ecological system at a high rate of function. And how we do this in part is by managing our canopy structure. The architecture of our canopy has, I can't overemphasize enough, we want to have good grasses underneath. We want photosynthesis on the ground all the way up to 100, 200 feet tall. We want photosynthesis over every single surface area. Once again, the sun-loving plants will like full sun. That's why we want to manage our canopy structure. We also want to maintain a canopy structure because if you look here, we can have everything photosynthesizing really well. Try not to be too shady like this is, and not too sunny, because then things will slow down. And too much sun, things will slow down. And too much shade. So somewhere right in the middle is our maximum optimum phase, and that's the savanna phase. So the deeper and more convoluted the canopy structure, the greater potential we have to sequester carbon from the atmosphere, and the carbon from the atmosphere is the energy. The energy is what drives our fertility cycle and releases the minerals from the soil, which makes our plants grow faster. this making any sense? How many times can I say this around and around? We got a closed canopy forest. Where's the green? It's way up top and is this little thin layer. This is growing nice, straight, tall trees. It's great. They are not growing as fast as they could. With more sunlight and more green, more canopy on each individual tree, the individual trees would grow faster. So maybe you could come through and remove a row, get some green into the forest floor here. Of course, you would have wanted to have done it before all these branches died off from too much shade. You do it when it's small and try to keep 2/3 of the tree canopy, at least 2/3 of the tree canopy in green, whether it's 6 feet tall or 60 feet tall. If 2/3 of that tree is in canopy, it's really humming along. And that means you have to remove trees through time in order to maintain that canopy structure. When we remove trees, that's wood for firewood, for building materials, for paper, for mushroom logs, for animal feed, and so on. We're harvesting the surplus, keeping it in a nice light stage, very productive. Right here, we've seen videos past couple of weeks. This is an extraordinarily productive system with very little care. No chemical inputs, no fertilizer inputs. It's yielded beef every year, pork every year, chestnuts every year from like year 5, grapes, hazelnuts, mushrooms, mulberries, elderberries, and so on, with no input costs. Also, we got lumber out of there, hybrid poplar lumber. I like to see this under the tree. I like to see this is Timothy. Timothy it requires full sun, so it's a sun-loving grass, and it also requires plenty of moisture in order to grow. And it's one of the, I think it's crack for cattle. They just love that stuff. A very sweet, digestible grass. So that means I have enough water on site and enough sun that the grasses actually will grow well. I got great tree growth and great grass growth. That's a system that's really humming along. Now back to the allocation of the tree. We already looked earlier that that the tree was sometimes putting 2/3 of its energy resources towards its root system. Well, this shows here that how much photosynthate it sends to its roots is sometimes up to 50% of its total photosynthesis goes right to the growth of roots. If we look at this chart here, when we have trees grown in low fertility soil, they put 36% of their energy into making roots. So in the early years, let's starve our trees a little. Well, it's usually pretty easy if you're going into like an old annual crop field because there's not a lot of nutrient cycling going on. So don't fertilize them. And maybe don't do much for weed competition. Force those roots to dive deep. That tree's going to panic. It may not grow tall, may not grow fat right away, but it's going to start putting as much of its energy to its roots as it possibly can to go deep. Whereas if you dig a $40 hole for a $10 tree, build that soil and give it all the compost it wants, it's just going to sit there. It's not going to put much of its energy towards making roots at all. It's just going to sit there and suck up the gravy and put on a lot of top growth. Well, then 2, 3, 5, 7, 10 years down the line, it runs out of that rich, easy nutrient, and then it doesn't have a root system worth a hoot. So if we want good, strong, healthy roots, let's have a little bit hungry in the early years and then build up our soil through time. One of the things that is also underlooked, I think, is roots and the organic matter of roots. This is the stump of a hybrid poplar that was originally logged off 10 years ago. Then last year it had been producing oyster mushrooms, but last year it was evident that the oyster mushrooms were kind of petering out, and the last sprout that came off the side, this had several stump sprouts that were coming off of it, but the last sprout kind of blew off in the wind, and so I decided to, because it's in the middle of a path, I decided to just drive right over it and mow it. But it's approximately 16 inches across, this stump. It's like, well, okay, all that organic matter, it was logged, it was cut off. Oh no, we've totally raped the site, it's gone. We stole that biomass, it was needed for the fertility cycle. Well, first of all, I've been contributing leaves and bark and stuff, for the 10 years prior, and then till before we logged it, and then another 10 years after that, and then we got mushrooms off of it for a whole bunch of years. But the root is still in the ground. And if we go back to this slide here, and if we had, 30, sometimes 50% of the tree as root mass, let's pretend it was 50% of this tree. The wood that I took away and built into a cider mill building, that's only half of the tree. Half of it was left behind underground, and that carbon is there for a long period of time. This is just a little chart. If we want to estimate the volume of that tree, if it was a 16-inch diameter tree, 2 of them would make a cord of wood. So that meant half a cord of wood per tree. A cord is 128 cubic feet. And if a cord of wood weighs about 4,000 pounds, a half a cord of wood is about a ton. Right there, there is a ton of hard, woody, organic matter under the ground that's feeding my decomposition rate and continuing to help mineralize the parent material of the soil. That's where fertilizer comes from. When we're reading research and stuff, and I showed this one a few weeks ago, and I want to do it again. This shows the rate of mineralization of the parent material, whether it's gravel or rock. And then this is the net productivity, net primary productivity. And you look at this chart, is that the more productive the plants are, the faster they grow, the more nutrients are actually released. Or it's also could be read otherwise, that the more nutrients that are released, the faster it grows. And what really bothered me about this says the Lake States region above ground productivity is correlated with the rate at which soil microorganisms release nitrogen from organic matter. Okay? But then what they say here, this relationship suggests that nitrogen availability imposes an important constraint on ecosystem productivity. Now wait a minute. How do you take that graph right there and immediately go from the first premise that this is just mapping above ground productivity with the rate of soil microorganism release of nitrogen, and immediately go to a statement that says, oh, nitrogen availability imposes an important constraint. What's imposing the most important constraint here that they don't even talk about is the rate at which soil microorganisms release nitrogen from soil organic matter. That's what this is saying, is that it's all about soil microorganisms and the organic matter, not nitrogen availability. So this yellow highlighted portion is what can lead to the simplistic thinking of, oh, let's just go ahead and add more fertilizer. Here's the action. This is what it's all about. You know, there's precipitation, dry precipitation, wet precipitation, drippage from leaves and lichens and epiphytes, the litter from leaves and sticks and bark, the decomposition of the organic matter with all of the organisms in here, and the mineralization of the parent material, which in this case happens to be rock, and the crushed rock right here. It's this whole system that is the key to terrestrial fertility and health and productivity of those systems. That's what makes it happen, and that's the system that we want to interact with. That's the process that we want to influence to strive toward higher productivity on our site. So our plant litter production above ground and below ground from sloughing of roots directly controls the timing of nutrients released from our soil, and that is what is constraining the growth of our system. Okay, so here again we see this slide. After a disturbance, we get this flush of soil nutrients. There's no trees there to soak it all up anymore. There's no grasses to soak it all up. That's going to go away. It's going to wash away with the water. How do we deal with that? This shows different ecosystem that has an episodic disturbance, which is either a fire or windstorm. And at that disturbance, all of a sudden we see below here, there's a loss of nutrient. Now we're aggrading, degrading, aggrading, degrading. This is natural, this is normal. Well, when all these nutrients flush and leave the system, leach from our system, why not have a crop ready at hand? Let's know that we're going to go in, we're going to disturb the system. We know there's going to be a release of nutrients, so let's plant a crop that capitalizes on that. This represents an annual crop, and I know last time I talked about this, I mentioned potatoes. Let's go ahead, and here's a stand. Let's go back in your imagination to that walnut, chestnut oak system. You wouldn't want to plant potatoes in walnut because potatoes don't really like walnuts. So let's go on to that walnut stand and let's plant corn, because corn is compatible with walnut. Let's cut down all of the black locusts, harvest firewood, logs for inoculating with shiitake. We've got all the chips that are now decomposing on the ground, and then we go in and we plant corn because we've got enough sunlight. When there's that nutrient flush from the decay of all of the litter and the roots below ground, our corn can suck it right up. Or if we do grasses, for example, after the disturbance, grass growth really peaks, and it helps to take up that excess nutrient that's released after the cut happens. Then as the trees grow back, they start to close canopy, they start to limit the grass. When the grass starts to go beyond what we want it, we remove more trees and the grass flushes, and so we have these two sine waves that are working with one another. In both of the situations that I showed, the two different clearings, one was removing the non-oak and hickories back up to where the pasture used to go, and the other one was in the walnut chestnut area, walnut oak chestnut area. With those two situations there, I let them get so far advanced that the grassy component almost disappeared. I try to get in there before the grass disappears completely. So you look down on a pasture and you don't want to see any bare dirt. When I start to see bare dirt, that's when I should get in there and start removing trees so I get enough light for that grass to grow. That's one way to keep that nutrient on the site. We're never going to understand the process of decomposition, release of nutrients. We're not going to ever understand that completely. I would like to see a lot more researchers study more the dynamics of chop and drop management in a semi-open silvopasture and or alley cropping agroforestry situation. So if you guys know any researchers or are researchers yourselves, that would be really helpful. I think if we learned a lot more about how to manage that decomposition cycles. So these are some of the slides I was on last time. It's with the simplest of tools. All you need is animal impact, fire, rest, technology, and then some understanding. We can participate in the optimization of life at any site on the planet, no matter where you are, whether you're in the high desert, in the savanna area, moist, dry, cold, hot, with very simple tools. Understanding the basic principles that we've talked about over the past 40 weeks, we can strive to have a system that's semi-open. It's a grassy woodland or a wooded grassland, however you want to look at it. We have an active decomposition process going on because it's that decomposition rate. Both of our deep roots in the ground that are decomposing, they're exuding sugars into the subsoil. Also, our woody plants are doing the same, and they're sloughing and building their fine roots over and over again. Our animals are digesting all the different plant matter and urinating and defecating. With these simple tools, we can participate in the optimization of life on any site on the planet. We don't even need soil right now. We can grow on the solid rock. We can grow food for humanity, habitat for wildlife, habitat for threatened and endangered species. And last weekend in Colorado, we were talking about a spadefoot, which is not even a toad, but it looks kind of like a toad. Its three middle toes are fused together, and it's used for digging in the soil. Critically endangered. Would just love to have some water management on Wayne's site. And also the northern cricket frog is another one that's right nearby their site that would benefit from that. We can have endangered species rebounding from the brink of extinction whilst we're simultaneously producing food, fuels, medicines, and fibers for people in systems like this. And guess what I had for dinner? I had some products of the decomposition rate and a perennial plant with deep roots that was very happy to suck up all of the nutrients released by the fungi in the decomposition rate in the soil, turning the parent material, the bedrock of the driftless area of Wisconsin, into morels and asparagus for Mark to turn into his handsome, lovely physiognomy. So does any of this, people, does any of this that we have examined in the last 40 weeks have any potential implications for the challenges of food production? Does this any way, if we have food production in almost anywhere around the world, from cliffs to caverns with perennial ecosystems, Can we help to feed an increasing human population? Do any systems like this, are any of these tools helpful for anybody in situations with declining per capita income? Just as an interesting aside, but it's not really an aside, for the past 30 years, in those 30 years, there's only been twice that I've earned more than the federal poverty level income. So I'm not a wealthy man, but I'm well fed. There's nobody that would doubt that. And I still manage 110 acres in southwest Wisconsin that we took from annual crops and pasture annual crops and pasture, and converted it into this, this thing. This picture was even taken 5 years ago. We should see it now. I have to get a good aerial photograph this year. Does a system like this, that's based on plants that have been through 4 different ice ages, global warmings and global coolings, does that have any potential to survive global weirding with the weather? What about fossil fuel availability? What if we don't have any more tractors available to me? As a matter of fact, I don't have a tractor available to me right now. I went out, I was going to plow up this field right here and plant annual grain on it because I never got a fall cover crop on it. I started up my tractor and one of the rear wheels blew out, courtesy of these black locusts over here. Big, huge thorn going through a sidewall. And first shop I took it to said, nope, sorry, we can't fix it. You got to take it to that shop over there. And they said, yep, certainly. It'll probably cost you less than $1,000. Like, whoo, we don't need that tractor in a perennial system. What happens if there's no fertilizer available? This corn and these soybeans, they're done. They're finished. This place is making its own fertilizer. It is providing habitat to 3 different kinds of weasels, 6 different kinds of amphibians, and so on. Health and nutrition, it blows corn and beans out of the water. Do we live a good life? I think I've lived a pretty good life. I've had a lot of fun, raised a family. The kids are pretty smart, doing all right for themselves. And I think it's beautiful. I think that's probably as significant as anything is the fact that this is like my grand art project and I've been having a blast. And I consider this to be real permaculture. We're restoring natural plant and animal communities. It's earth care. Growing tons of food for humans. We're selling food for people. We're part of a collaborative business venture with the American Hazelnut Company in Organic Valley. We volunteer at the local schools, nonprofits. That's real people care. And we're reinvesting in the ecological health of the planet, and we work to establish equitable relationships and all activities. That's a real fair share, whatever that third ethic is. And I guess I didn't mean to kill that last one. I guess that's it for tonight, and that's it for this particular segment. And do we have any questions right away? So here's planting young trees in a grass meadow. Would I plant directly into the grass, or would I do any preparation to give the trees a better survival chance? I plant directly into the grass or meadow. And if a tree cannot tolerate living in the grass or meadow and it dies, good riddance, because I want the ones that can. I'm not interested in babying little sissy plants that are going to die on me. If you look at all the trees in this picture on the computer screen there, there's probably, I'm guessing, I don't know, there's probably 100,000 trees there, and I'm willing to bet there's probably as many that didn't survive. And that's part of how nature works. And I don't remember what webinar series it was. It showed, this area that had been disturbed, and then the oodles of these little sugar maple seedlings that grew, and then you could see some of them that had grown 2 or 3 years and survived. Some of them were like 5 or 6 years and survived. But the majority of those plants in nature don't survive. We humans have gotten into this thing that we think that you're supposed to plant one tree and it's going to survive, for 100 years or whatever, and it's going to be the be-all, end-all. Well, that might be the wrong one. We want to have the exact right genetics, so we want it to survive the rugged conditions that we abuse it in. We want it to reproduce young in its life, and we want it to reproduce and have lots of seed or fruit, seed or fruit, not cedar fruit. And so if we plant more trees than others would, and then let some die, because we're not interested in the ones that can't really tough it out and rough it out, that's how we find the superior genetics of seedlings. One to some of my open canopies forests have nothing growing under it. Let's see, Ray. Ray, aren't you in Missouri? Is that the case? I think Ray was in Missouri. A lot of that oftentimes has to do with moisture, is that you may have too many trees. And let's go to like Wayne's place in Colorado. There's places where he has really runty, stunty ponderosa pine, and it's open, and there's some grass there. You may have really shallow soil, like hardly any at all. It might be rock, and it may be just lack of moisture, and it's probably also limited nutrition, and that's a function of your decomposition rate, and of course, which is also a function of water. So we have to have adequate water, adequate decomposition rate, and then that'll help to create optimum nutrition. How do we get more water on the site? Well, maybe there's a little bit of earthworks that would be involved. Maybe that would be, you know, managing more organic matter with full ground contact. Maybe that actually means eliminating a little bit of, you know, some more trees. There's a lot of places. Let's especially go to like southern Missouri into Oklahoma, where there's hardly any soil nutrition. I'm thinking right now of northeastern Oklahoma, southern Missouri, how a lot of the hills, they're just crumbled, crushed rock, and there's really no soil. It's just crushed rock. So when there's plenty of rain, 45 inches of rain a year, it just goes right through. So we need organic matter in that soil, which means dumping down lots of grass seed and having maybe half of it die, doing a little bit of earthworks, maybe making some brush gabions to collect organic matter. And maybe it is a function of sunlight, open up a little bit more. I don't exactly know for sure. And then endangered species on one of our sites would mean government coming in and shutting down the agriculture to conserve the endangered species. That's actually one of the reasons, Mary, why we want to have inventories, species inventories when we get started. When you start your project, take pictures of your site. And also explain what it is that you're doing and why that you're doing it. I do recall that once upon a time, it was one of the videos, one of the first Sepp Holter videos that ever came out. It was like 60% of all endangered species in Austria had representatives on Sepp Holter's farm. Well, then follow-up research showed that about 50% of all endangered species, total numbers of creatures, were on Sepp Holter's farm. I thought that was fascinating. Then there was in Nebraska at the Arbor Day farm a number of years ago, probably 10 years ago, the whole bunch of people were participating in trying to use a straddle harvester, a blueberry harvester, to harvest hybrid bush hazels. And it did work, and one of the people who was observing this was an insect guy, an insectologist or whatever they call you guys, and he was noticing walking sticks coming out of the back of the harvester and crawling out of the hazelnuts. And, you know, he immediately was like, stop, stop, stop. You know, walking sticks are an endangered species. You can't, you know, you can't do this. You know, you got to stop. You're hurting the walking sticks. But the walking sticks were walking right out. And he said, wow, that's a lot of walking sticks. And as we went down the road, he's like, I've never seen so many walking sticks. It's a big insect that looks like a stick. He then did follow-up research and came back to the site and discovered that in Nebraska, the walking stick is an endangered species. Well, like 90% of all individuals of the walking stick, you know, genus and species were in that 9-acre hazelnut field. So yeah, if we're doing restoration work, we will restore habitat for the species that were dependent on it. And if we do our base background inventory first, show what was here, then show that by producing our agriculture this particular way, we're also providing habitat. We have more numbers as we're going on than we ever did before. I have more weasel species living on my property now, even though I'm currently farming it actively. I have ground nesting birds that weren't there before, et cetera, that weren't found in a corn or soybean field, that aren't found in a situation like that are here. Yes, every once in a while I chop up a nest of horned larks with my mower. I don't think I've ever run over a weasel or anything. So yeah, we will have issues. My biggest concerns are as we create more rich and abundant habitats, let's start to get mountain lions setting up camp in our particular farm that then go down to the local kindergarten and start eating kindergarten children. Then we really have problems. All of these problems that our ancestors had, the reason why they wiped out all the wildlife was because it actually did cause problems. How can we restore the ecosystems of the planet and figure out going forward how to learn with the how to live with wildlife? So there's a full-blown water management plan on the cards for Wayne's property. It is underway. It is underway. Yes, it is. Tractor tire, 4-inch tear. Actually, this tractor tire is different because it's a 10-year-old tractor. It's a 40 horsepower tractor, and the flail chopper that I use is rated for a 40 to 80 horse tractor. So it's just a little bit too big. My tractor is the smallest tractor that even spin that thing. And so what happens is the 3-point hitch wiggles back and forth, and so the passenger, the left side inner sidewall has just been consistently scored through the years, and it's gotten eroded really, really fine, so a patch won't fix this thing. And then all that happened was a locust thorn went through that already abraded thin sidewall, and it was irreparable. All right, I'm about to head out for the evening. Let's have one more. How do you proper spacing between the trees which you plant? A few weeks back, I believe 3 or 4 weeks ago, there was a session where it talked about tree spacing and stem diameter. There are tables that are well known in the forestry industry that farmers and orchardists don't even think about, which is part of the crossover that we're doing here. If you look at those tables, the number of stems per acre versus stem diameter, they kind of tell you how many stems per acre to have. And when you have a tree that's this big around, it has a crown, a canopy that's about yay size. And if it's this big around, it's a canopy that size, and there's only so many trees that will fit per acre. So by just doing an internet search for a number of stems per acre for stem diameter, that'll give you a good idea of that. So always plant on the heavy side, plant way too many, and then you remove through time, because when you remove them, that's the stuff that you chop and drop, and that's part of your fertility cycle, or that's the stuff that you remove for firewood, or that's the stuff that you remove for basket weaving, or for making mushrooms, and so on and so on and so on. And we don't know which ones will survive and won't survive, and that's why we want to have too many going. So thank you, everybody, for being here tonight, and we'll be back next week. Probably going to be starting to talk about a project going on in the Netherlands, one in Wisconsin and one in New York State, about conversion of a